Today we'll cover system design, CPU processing and assembly operations, focusing on how manual assembly coding can enhance performance. The control bus manages system components using signals like read-write, memory enable, address latch enable, and clock signals to coordinate processor and memory operations. The data bus is a bidirectional communication pathway that transfers actual data between the processor, memory, and peripherals during read and write operations. Memory operations involve the processor using the address, control, and data buses to read from or write to memory locations, with the control bus managing the direction of data transfer. Memory operations can be performed using system calls like mmap for reading and writing, memcp for data transfer, IOCTL for device control, and accessing physical memory directly through /dev/mem with caution. Logical memory maps provide a virtual address space for processes, dividing memory into separate segments for efficient operation. Physical memory is mapped to logical memory through paging and segmentation, using a page table to translate virtual pages to physical frames, allowing for efficient memory management. A program is a set of instructions stored on disk, while a process is the active execution of that program, managed by the operating system, which allocates resources and executes the code. Modern CPUs employ enhancements like pipelining, superscalar execution, branch prediction, out-of-order execution, and multi-level cache memory to improve efficiency, speed, and overall performance. CPUs use two types of registers: general-purpose registers GPRs, like EAX, RAX, and R0, R15 for versatile operations, and special-purpose registers like instruction register, program counter, stack pointer, and flag status register for specific functions. CPUs have specialized registers including segment registers, CS, DS, SS, ES, FS, GS, for memory segmentation, and floating point registers, FPU, XMM, VFP, for efficient floating point and SIMD operations. CPUs have additional specialized registers, including control registers, CR0, CR4, MSR, for system configuration, debug registers, DR0, DR7, for debugging, instruction pointer, RIP/EIP/IP, for program execution, and vector extended registers, YMM, ZMM, for advanced SIMD operations. Segmentation divides logical memory into segments, code, data, stack, with each segment's base address and limit stored in a table, and translates logical addresses to physical addresses by adding the segment base to the offset. You can use the MOV instruction in assembly language to transfer data between registers, memory, and immediate values, with variations like MOVX and MOVZX for sign extension and zero extension respectively, to handle different data sizes. The MOV instruction with byte PTR specifies the size of the opera and being accessed in memory, ensuring that only a single byte, 8 bits, is moved between registers and memory, preventing potential data size mismatches. Assembly language instructions for unary and binary operations include INC, DC, NEG, ADD, SUB, MULE, DEV, IMULE, and IDV, which perform arithmetic operations on registers and memory, with specific conventions for operand placement and result storage. A stack is a LIFO data structure that grows downward, with the stack pointer, SP, registering its top, and components like base pointer, BP, and frame pointer, helping reference variables and manage function calls in assembly language programming. In assembly language, the stack is utilized for function calls, storing return addresses, local variables, and arguments, and data is managed using push and pop instructions, which add and remove values from the stack, respectively, while updating the stack pointer. In assembly language, registers are saved and restored by pushing their values onto the stack before modification and popping them back after use, while stack frames are created and managed using base pointers, BP, to track function calls, parameters, and local variables. The RET instruction returns control to the calling function by popping the return address from the stack and jumping to it, effectively ending the current function's execution. Subroutines in assembly language are reusable blocks of code that perform specific tasks, called using the call instruction and returned from using the RET instruction, which manage the stack to facilitate code reuse and structure. Subroutines receive parameters through registers, stack, or memory, and use a stack frame to manage local variables, return addresses, and previous frame pointers, allowing for efficient and organized code execution. This code example shows a subroutine my function setting up a stack frame, executing code, and returning to the caller, demonstrating typical assembly language subroutine structure and functionality. MASM and NASM are two assemblers with differences in syntax, MASM's Intel syntax versus NASM's concise syntax, platform support, MASM for Windows, DOS, NASM for multiple platforms, and macro capabilities, MASM's more powerful built-in macros. MASM and NASM differ in object file formats, MASM, COF, OBJ, NASM, ELF/COF/bin, and licensing, MASM, proprietary, NASM, open source, making NASM a more flexible and popular choice for assembly language programming. To integrate assembly code into a C++ project in Visual Studio 2022, create a new C++ project, add an assembly file, DSM, with MASM syntax, compile it to generate an object file, obj, and link it with your C++ code using extern declarations. Integrate assembly code into C++ projects in Visual Studio 2022 by adding an assembly file, compiling it, linking the object file, calling the assembly function, and configuring the project, or simply download and open the MHM Rajput / Let's C Assembly GitHub repo in VS 2022. This C++ code uses inline assembly to multiply two integers, a and b, using a loop, storing the result in the result variable, and then prints the result to the console. The code performs division with repeated instructions, storing the result in C and the remainder in D. Journey of 4 arithmetic operations, addition, subtraction, multiplication, and division, performed using assembly code within a C program, utilizing registers and memory operations to store results in variables A, B, C, and D. The C programming language compilation process involves 4 stages: pre-processing, compilation, assembly, and object file generation, transforming the source code into an object file containing machine code and data. The final stages of the C programming language compilation process involve linking object files and libraries, loading the executable into memory, and executing the machine code instructions to perform computations and produce output. The process involves assembling hello.sm into a 32-bit ELF object file hello O using MASM, then compiling and linking main C with hello O using GCC to create a 32-bit executable main, which is then executed to produce output. This assembly code defines a function write_message that prints a null terminated string to the console. By iterating through each character, using the Linux system call int 0x80 to write each character to file descriptor 1, stodout. The assembly code follows conventions for interoperability with C code by preserving registers, EBX, EKEX, EDX, managing the stack, saving the base pointer, EBP, and allocating, deallocating local variables to ensure correct function calls, returns, and communication with C code. Implementing recursion in assembly language can be inefficient due to the overhead of saving registers, pushing, popping arguments, and the risk of stack overflow, leading to increased execution time and code complexity. Utilizing hardware-accelerated instructions like SkyESB, REPNI, CMPSB, StereoSB, and MoviSB in assembly language can significantly optimize string operations and achieve faster execution times compared to C or standard assembly implementations. These declarations allow C programs to interface with assembly language subroutines for string length calculation, string comparison, memory setting, and memory copying, enabling efficient low-level operations in daily routine tasks. The mem_free assembly function securely clears sensitive data from memory by filling an array with null values, using the rep_stosb instruction to prevent data leaks and enhance application security and stability. Download code from GitHub repository. Place the Irvine folder in the C, drive as demonstrated. Open the code with Visual Studio 2022. Expand the code files and change the system architecture to x86. Rebuild the code. Examine the multiplication example with a loop in assembly. Compute the length of a string with a loop in assembly. Perform a swap using stack operations in assembly. Observe the time saved in a loop by avoiding excessive pushing and popping of stack operations compared to recursion. Review the accumulate function, which takes a C array and returns the sum in EAX. Send C string pointers to assembly by big number class and receive a pointer to the string sum in return. This pointer stores all data members in C and continuous memory, and can also be passed to assembly. Learn how to free memory of local variables so that it can be accessed by other programs after the job is done. Open the x86 MASM.bpinb file in Google Colab and run the setup. Review a Hello World program which pushes and pops EBX, ECX, and EDX to smoothly transfer control of stdout back to C. Experiment with custom printf functionality. Compile all assembly code into object subroutines and use them with C.